Okay, these the different types of polarized and polarized, non-polarized, and variable capacitors with their schematic symbol. The first one, it's polarized capacitors, where we have electrolytic capacitor, we have tantalum capacitor, we have tantalum siding capacitor, we have surface mounting device capacitor, and their corresponding symbols are three, this one and this one and this one. So the symbol of electrolytic capacitor, polarized capacitor, it can be this one with the positive sign, or it can be one end it's open, one end is closed, so the open end is positive. And this one, the closed or the shadowed end, is negative always. Or it can have this schematic symbol. Then another types of capacitor, this the different types of non-polarized capacitors. They don't have polarity. You can represent them, for instance, this one, this is electrolytic, this is ceramic, actually that from here, from ceramic, and that is polystyrene, and that is surface mounting non-polarized capacitor. So the symbol might be that one, so that one, so that one. But remember, the other ones does not have a positive sign to indicate the terminals, right? And then the last group of 14 is a group of variable capacitors. So this variable capacitor, they have two terminals, but they have also a set terminal, which you call the adjustment terminal, to adjust, actually allow to adjust the capacitance to the capacitor. So all of these are three examples of 14 variable capacitors. We don't use them oftenly in electronics compared to polarized and non-polarized capacitor, but it's better to know them. The schematic symbol of variable capacitors, you can see that this the symbol, one of the symbol, that one is this one, that one is this one. So you may use 8 of them actually in still representing the meaning. So whenever you find in the schematic circuit diagram, in the schematic analog circuit diagram, or less found in the schematic digital or logic circuit diagram, so actually that you have to understand that they represent variable capacitors. So the aim, we are not going to cover about the variable capacitors, but we want to introduce into the mind of the students actually to know that, in the world of today, we have variable capacitors and they perform particular function. So if that's the case, thank you for this moment of demonstration. How are you, everybody who is watching this video? I would like to take this opportunity to welcome all the physical students and even online engineering students who would like to join with this program. My name is Olenjolain, and I'm very glad to have you today. And I want to tell you that I have a good news concerning about electronics engineering. So I would like to ask you to stay tuned and stay connected with this. So I would like to take this opportunity to welcome you again into the continuation of our programs that call the Fundamental of Practical Electronics Engineering. And we are in chapter 5 that called the capacitors. We have covered the chapter 4, which is dealt with resistors. And now we are going to the next level of the capacitors. But I want just to say a couple of the things before we go, or before we start our today's workshop, which is actually be workshop 5/1 or 5/1. Because we'll be having workshop 5/1, workshop 5/2, etc. So one thing which I want to tell you that whether you are whether you are a technician or you are a student in any of electrical engineering field, these contents will be important for you, because actually will be transforming your understanding from the knowledge of mathematics and science at the background that you have covered in ordinary secondary education level, or you have covered in the advanced secondary level. And then once I will be taking you step to step to transform from the moments or from your experience of mathematics and science into the experience of electrical and electronics engineering. So if you're a student pursuing electronics engineering, you are warmly welcome. Students that pursuing either diploma or bachelor in telecommunication engineering, this program is very important for you. Also, if you're students who pursuing mechatronics engineering, or pursuing biomedical engineering, or pursuing electrical engineering, or pursuing renewable energy or biomedical, computer engineering, maybe hopeful IT guys, this is not a suitable program for you. And even computer scientists, this is not important program for you. We'll be having some other courses for computer programming. So let us right now go directly to our today's workshop. But another thing which I want to tell you that this is very interactive program. It's more practical program. We'll be teaching you the theory behind the capacitor, for instance, in this case, or the theory behind the discrete electrons components, and then we'll take you into the simulation, and then we'll take you into the practical part. So this is the theory of capacitors, but we'll be taking you into the simulations of capacitors, then we'll go for the practicals of capacitors. So today we are going to cover about capacitor, and another thing which I want to tell you that before we start our today's class, this is a very interactive class. In case you have any question, don't hesitate to ask in the comment section or in the chat. And don't hesitate also to raise the hand for the physical student. How are you, student? Okay, those are the few students who have joined me in this program and are well connected. And actually, they'll be helping you to ask you some questions in case that something is not clear. But for the online students, make sure that you use the comment section to ask you questions as well. We'll be trying our level best to answer your questions as well as we can. Remember that Olenjolain does not know everything about capacitor. I just know a smaller portion of it, but I have a responsibility to teach others. So if that's the case, whether you're Tanzanian, let us go into today's business. So these are electronics components that you are going to study about. So this we call it a supercapacitor. It's called the supercapacitor, which is capacitance is 470 microfarad. So let me just show you some of them. This also it's a actual that we call non-polarized capacitor, and then this is electrolytic capacitor, which it has it's 470 microfarad but 63 volt. Then we have also some electrolytic capacitors like this one. We have also ceramic capacitors. This is called ceramic disc capacitors. We also have some other form of the capacitor like this one that we'll be discussing about. And also we have another form of the capacitor just like this one. So you're going to discuss, also we have another form of the capacitor just like this one. This is called the organic capacitor. And also we have another capacitor which in this form, right? So this is another type of the capacitor. All of them are non-polarized capacitors, but they have different dielectric materials. But also you can have some electrolytic capacitors like this one. So this is the electrolytic capacitor. We are going to discuss about it, or I'm going to introduce about them. Also you have this one. This is the ceramic capacitor. This is a ceramic disc capacitor. We are going to discuss about them. So simply, this is the collections of the capacitor, of the different types of capacitor that we are going to discuss. So I want just to encourage you and actually to motivate you about what you are going to discuss. So if that's the case, let us go into the workshop 5.1. So this is workshop 5/1. Let us just call capacitors. That's the title of this workshop. Capacitors. Say capacitors. Class A capacitors. Okay, so in this workshop, I'm going just to introduce you about the big picture of the capacitor, but in the context of the practical, not in the context, and with the context of engineering per se. I'll be just reminding you what the capacitor, what are the categories of capacitor, why are we using capacitor, what are the categories of capacitor, why are we using polarized capacitor in DC power, why are we using non-polarized capacitors in both AC and DC power. So that's what we are going to discuss in actual. And then in the next workshop, I'll be teaching you about polarized capacitors. Are we together? So the fundamental question here, or the first terminology that you like to understand, we are the engineers, we just need to understand two main terminologies or three main terminologies in the capacitor. Just we have to understand two main terminologies of the capacitor, and then we have to understand two measurement parameters of the capacitor. The first terminology is the capacitor. What does it mean? What's the meaning of the word capacitor? And the second terminology is capacitance, right? And in case of the measurement parameters, also we'll have additional third terminology that called the rated voltage or voltage rating. We had the power rating in resistor, but in capacitor you're going to have voltage rating. Are we together? So those are the key important words. Also, okay, in engineering we might think about the electric materials, but it's not a great deal. We have already discussed in science especially in physics science. So possible that we know, because we can categorize capacitor into 4 categories. If you do remember, we had the paper capacitor because the direct material is paper. We have what again? We have mica capacitor because the direct material is what? Mica. We have electrolytic capacitor. Why? Because what? Because the direct material which has been used is what? We have paper capacitor. We have mica capacitor, we have ceramic capacitor, we have also electrolytic capacitor. The difference between those 4 capacitors is the type of the electric materials, right? Because the capacitor is nothing actually. We say that it's just arrangements of the 2 parallel plates and the electric material are in between them, right? Yeah. So, the first terminology that you like to understand is the word capacitor. Class, say capacitor. Say capacitor. So today you have to think about capacitor, and I would like to encourage you, you have to think that the word capacitor until you dream it one night. So what is capacitor? If your friend, or if your student, or if your young brother or young sister ask you, my sister, my brother, what the means of the capacitor? So what is capacitor? There's a different way that you can define a capacitor, but let me just share with you a few of them. A capacitor is electrical, so it's electric, or is a passive. Let us just start with this one with this word. Is a passive 2-terminal capacitor. Also it is 2-terminal, just like a resistor. 2-terminal electric or electronics component which is used, or that stores electric charges or electric energy. Let's say that electric energy in form of electric field. Form of electric fields. So a capacitor is a passive 2-terminal electric or electronic component that store electric energy in form of electric fields. This is one way that you can define. What is a capacitor? First of all, it's a passive. Say passive. Passive. In electronics and electrical, we have passive and the active. So a capacitor itself, it's what? Passive. So it's a passive, and another keyword, it's a 2-terminal. How many terminals does it have? 2 terminals. Add S as a plural. 2 terminals, electronic or electric component that store electric energy in form of electric fields. So when you say that in forms of electric field, in electrical engineering we have electric fields and magnetic fields. Right? We have electric fields and what? Magnetic fields. So this one to store electric energy in form of electric fields. When you say electric field, it means electric strength. This is the one way that you can define a word capacitor. In other words, a capacitor can also define a word capacitor. A capacitor is a device. A capacitor is a device. A capacitor is a device that is used. Is a device that is used to store charge consisting consisting of one or more pairs of 40 more pairs of conductors. Conductors separated by dielectric material. By dielectric materials. This is another way that you can define. So a capacitor is a device, say device, that is used to store electric charge. But also its structure, it consists in what? One or more pairs of 40 conductors separated by what? The electric materials. So this is, with this definition, it's actually explaining the function, the primary function of the capacitor, but it's also explaining what? The construction of the capacitor. That the capacitor consists of a pair of 40, a pair of separated what? Conductors, right? And also in between of those pair of separated conductors, we can you can find out the electric materials. Are we together? So now the word capacitor, now we don't mean about device as a device. The word capacitor means, according to the dictionary, what they means is the ability to hold something. Is ability to hold something. So the word capacitor means that it's ability to hold something. If we call you capacitor, capacitor Ruben, capacitor Jacqueline, capacitor Farid, capacitor John, it means that you have ability to hold your tea. What can you hold? Ask your neighbor. What can you hold? Eh? You have ability to hold your charge. Eh? So if the word capacitor means that is ability to hold something, so simply say that also the capacitor as a device, the capacitor has ability to hold what? Electric charge. This is what we taught you in science, in physics science, and also we still remind you in order to move on. So when we consider this definition of the capacitor, simply say that here it's just the constructions of it, just to remind you what we taught you in physics science, especially advanced physics science, where we learned about electrostatic. Do you remember it? Do you still like it? Or you don't like it because it had Gaussian's equation, it has Gaussian's law. So this is positive plate of the capacitor, and this is the negative plate of the capacitor. And then here we had what, if you do remember, how do you call this one? Farid, how do you call it? Ruben, how do you call these lines? Ruben has forgotten. He was expert on drawing them, but he has forgotten nowadays. These we call them electric field lines. Electric field what? And these electric field lines always electric field lines start from the positive plate towards the negative plate, right? Huh? Is it true? Because if you just want to remember, we had a positive charge and negative charge. So positive charge actual produce what? Electric field. If you just want to remember, in case you forgot. Right? A negative charge actual that receive what? Electric field. That's why that unlike charge attract. And like charge repel. Are we together? Eh? So these are electric field lines. So stop writing and stop drawing. This one, we call it a positive plate. Positive plate, and this should be a conductor. Should be what? As we say, pair of what? Of conductors. So positive plate, or we call it a positive conductor. And this one, it's what? It is negative plate, or negative what? Conductor. Okay? And then this one, we call them what? Electric what? Field lines. So stop writing and stop drawing. Just look and let us label together. And then here, between these two parallel plates, this region, this is the region where we have to place what? The electric what? The electric material. The electric materials. What the function of the electric materials is to increase capacitance of the capacitor. Is to increase the ability of the capacitor to hold the electric what? Charges. Are we together? So this is figure 1. We say that the structure of what? Of a capacitor. Don't you draw yet? Of a capacitor. So listen. If a capacitor is called the electrolytic capacitor, say electrolytic capacitor, it means that it has two parallel plates. One plate is positive, the other one is negative. But between these two parallel plates, there is a material we call the electric material. And the electric material for electrolytic capacitor, it's electrolyte. Say electrolyte. Say electrolyte. So you remember about electrolyte that you learned in electrolysis of chemistry form 3, right? And also learn electrolysis in what? In electrochemistry, right? In advanced physics form 6. So with electrolyte, so you know the property of electrolyte, right? Within it we have what? Cations and what? And an ion, right? Yeah. So something happened there, and when this positive plate and negative plates have been connected, this is polarized capacitor. They have been connected to the source of DC power. Then we can find that it can hold the charges, the electric charge. If the capacitor is called the paper capacitor, but this is for electrolytic. Just I want to give you a picture of the name of the capacitors in relations with the electric materials, right? If the capacitor is called the paper capacitor, it means that the electric material used is what? Paper what? Paper. So the paper, like this one. If the capacitor is called the mica, the dielectric materials which has been used is what? Mica. If the dielectric material, or if the capacitor is called the polystyrene, I mean the dielectric materials, it's organic compound. Are we together? So remember that this is polarized, and you can, in this workshop, you will understand the theory behind that what you've been teaching you in O level and A level advanced physics. We have been teaching about electrolytic capacitor. Why? We used to draw the positive plates and negative plates. So this is polarized capacitor. Why? Because there's polarity. When you talk about non-polarized capacitor, however, that will cover it in intermediate of practical electronics engineering. When you talk about polarized capacitors, we don't have these positive and negative plates. Right? It does not have polarity, but it has two plates. Are we together? Yeah. There's two plates. So this we can say that the structure of of a polarized capacitor. Let me just think of a polarized. Let me add something, add value on what you know from your physics science. A structure of a polarized of a polarized capacitor. So the structure of non-polarized capacitor is similar to that one, but it won't have polarity. It won't have what? Polarity. So it has two plates. So you have these two plates. Then say that, and this is the positive plate. So this is first plate, and this is the second plate. And here we have the electric material. Electric materials. So this is figure 5.1. This is figure 5.2, the structure of non-polarized capacitors. So I think the terminology of capacitor is clear. In case it's not clear, you can ask a question. But I believe that I have reminded you what we have taught you in physics, from 2, the first topic that called static electricity, and also in electrostatic, the first topic in advanced physics from 5. So now let me take you into the second important terminology that's called the capacitance. If you have any question about capacitor, you may ask. But remember that with this program, we are just learning the fundamentals of the capacitor. So we have to limit ourselves. And we assume that all our students have a prior knowledge of capacitor. We are just reminding them quickly, and then we'll keep we'll keep focus in practical. So we have a word called number 2. What is capacitance? That's the question we have. Class A, capacitance. Online and the physical students say capacitance. Say capacitance. Say capacitance. So capacitance corresponds with the word resistance. The simple way to distinguish this terminology, resistor, it's a component. And capacitor also, it's a component. But resistance, it's a property. And capacitance, it's a property. Are we together? And as I taught you in resistor, I told you that you have to master as electronics and telecommunication technicians or engineer, or as mechatronics and computer technicians or engineer, or as electrical or biomedical technicians or engineer, or as telecommunication or communication engineer or technician. You have to master 3 discrete electronics components that we call them resistor, capacitor, and inductor. Why? Because most of the sensors that we have in electronics, and especially embedded electronics, they use the property of resistance, capacitance, and the inductance in order to detect a real-world physical quantity. Can I repeat? Let me repeat. I would like to tell you that we are learning the property of capacitor, and I've told you the property of the resistor. And later on, it's possible that we can touch a little bit about the properties of what, of inductance or of inductor. But remember that when we are teaching you about these properties, the property of resistance, the property of capacitance, the property of inductance, you as electronics and electronics or telecommunication engineer or technician, you have to listen and have to make sure that you understand. Why? Because this is the property. It's not the only property that we find in these passive electrical components. No. We may find them in different materials. And we use these properties actually in sensors and even in transducers. How are we using this property? Because remember that if this is the property, we cannot find this property only in the capacitor. We may find even in another materials. Because the function of the sensors is actually to sense the real world situation or the real world condition. Okay? So the sensor might use the property of resistance to detect that real world condition or situation. For instance, a temperature sensor might use the property of resistance to vary or to show the variations of temperature in according to the real variations in the real world. Are we together? Are we together? Maybe pressure sensor can use the property of capacitance actually to measure the pressure, just the atmospheric pressure, or to measure the body or the human pressure. Are we together? For instance, you might find that we have sensors which call them the pH sensor. pH sensor actually the sensor which actually detected the pH of the because you know that pH is the degree of what? Acidity or alkalinity, right? So you might find that sensor, it uses the property of what? Of either resistance or capacitance or inductance to measure the pH of the particular solutions or liquid. Are we together? We have also sensors which actually detect humidity, or maybe detecting just we say that the presence of the person, so detecting the soil moisture, or detecting, we have also some sensors that detecting the amounts of the gas, maybe amounts of the carbon dioxide in this class. So when you study the functionality of those sensors, I believe that the property that you might find is one among the three: resistance, capacitance, inductance. It does not mean that within they have resistor, or within those sensors there is the capacitors, or within those sensors there is the inductor. No. But there are materials which have the property of either resistance or inductance or capacitance, or two in one. Are we together? Are we together? I know you're expert on defining what the means of capacitance. But now that the foundation, it's good. So now, think to yourself, where can I apply the knowledge of capacitance in solving a real world problem? Are we together? Are we together? Okay, so what is capacitance? Simply, we say that capacitance is a property of a material, or it's a property of a capacitor that is defined as the ratio of electric charge on conductors to the potential difference between them. So capacitance, I know the second part of this definition, separating, I know that you know it. Capacitance is a ratio of electric charge to the potential difference, that's all. But possibly you have never known or you have never heard that capacitance is the property, right? Because if you say you just have a knowledge of capacitance is the ratio of electric charge to the potential difference, you limit the concept of capacitance in the capacitors only. Why? Because in the capacitor, at the point where the capacitor, it's a component that, or it's a device that is store charge, right? Where you can find charge. But also you can find the potential difference between the two plates. But today, just remember this for the rest of your life. Capacitance, it's a property. Property of what? Of a material capacitor. That defines as what? Ratio of what? Electric charge on conductors. On what? We means about this pair of conductors, right? On conductors. To the potential difference between what? Between them. So it means that if the capacitance is a property, that material should have electric charge. Or when electric current flows through that material, then that material will have what? Electric charge. But also it will have what? Just the two conductors. In such a way that that material or that part or that material should have what? The potential difference. So it means that if there is electric charge, when electric current flows through that material, and also there is the 2 points where we call them the two conductors, where you can get the potential difference, then that's why we say that this material has what? A property of what? Capacitance. Are we together? Is it clear or it's not clear? Huh? So we can have a material. So for instance, this capacitor, if it is not charged, if it is not what? If it's not charged, it has been discharged, completely discharged. So within, we have two conductors, and also within, we have what? The dielectric material, right? So for that case, we say that within it, we don't have charges on the conductors. And also we don't have potential difference between the 2 points, because those 2 conductors are this one, which have been extended. The 2 conductors that we are talking about are this one, which have been externally extended. This pin, this terminal, and this one. Those are the 2 conductors. Right? Those are the 2 conductors. If there are 2 conductors, it means we can have potential difference. But if there is a supply of electric power or this capacitor itself, it has charge. Are we together? So if you have a capacitor like this one, which is full discharged, then within it, it has 2 conductors, and within it has a dielectric material. Within it has 2 terminals. But within it does not have electric charge. Right? And also it does not have what? Potential difference, because there's no charge and there's no source of power. But this one, it's a material, it's a device, which has that property. So when you supply DC or direct current, when you supply electric energy, then from there, you can find that those conductors will allow the flow of electric currents, and then the electric charge will be stored, will be held within this one. And because it will be held, then we are going to have a potential difference between the 2 conductors. Are we together? So this is the capacitor. But you can have some other material which the structure is not the capacitor, but it has what? The property of what? Capacitance. But that material also will not have the properties of capacitance if there is no stored charge, and if there is no potential difference between the 2 points. Class, are we together? Are we together? Are we together? So if you say that a particular sensor detects a real-world phenomena by using the property of capacitance, then that sensor, within it, it has the conductors, it has what? Within it, the electric material, or it has the property of what? Of capacitance. But once we supply electric energy onto it, then you can find the property of capacitance start to work. It's just like a resistor. A resistor, within it, it has a resistance, right? But that resistance will never work until the current has been supplied. Are we together? Are we together? So we just remind you mathematically how do we represent the concepts of the capacitance. Just to recall, we taught you that the quantity of charge is equal to capacitance times what? Times potential difference. So to compute capacitance is equal to quantity of charge over voltage. So whereby, just to remind you, whereby Q representing quantity of what? Quantity of charge. Then where V represents what? Potential difference. Potential difference or voltage. And where C represents what? Capacitance. So mathematically, because you say engineering is all about numbers, it's all about formulas, it's all about equation, so it's better also to remind you about the mathematical equation of the capacitance. So capacitance is just the quantity of charge over voltage, because we'll be discussing this one later on as one of the measurement parameters of the capacitor. Is it clear? If you have any question, don't hesitate to ask. For the online students or online community, in case that you have any question, don't hesitate to ask in the comment section. Again, another important information before we continue to the next part about the capacitor. Let's just recall, or let me just remind. So, which type of the energy that the capacitor store? A capacitor store the electricity, class electricity, electric energy. Capacitor store what? Electric energy. So let me remind you, especially there are some students who are come from A level or advanced secondary education level. For them, it's just a reminder. For the students who are come from ordinary secondary education level, this is your first time. Stop writing. We say that the electric energy stored in the capacitor, which you call E, this is equal to a half times what? Times capacitance. We say that a half QV square. A half QV square. Half QV square. That's a half I square L. Then say a half times quantity of charge square times capacitance. So electric energy, we say that this is a half Q square C. No, V. Sorry, V. So this is the formula of electric energy stored in the capacitor. Half square of the quantity of charge times what? Voltage. And it's corresponding for the inductor, you know that is what? A half I square L. Okay, so this is just to remind you about the electric energy. Then, after we have covered about that, we say that what is the SI unit of capacitance? That's very important. SI unit of capacitance is what? Pi. Farad. So SI unit of capacitance is farad, which you use capital F. What are the other units? But most capacitors are not made in farad. So most capacitors are made in other units of capacitance. Other units of capacitance are, the first one is millifarad. Milliwatt. Say millifarad. Say millifarad. Remember that most of the capacitors are manufactured in terms of microfarad, nanofarad, and picofarad, except supercapacitors. Supercapacitors, you can find a supercapacitor of 240 farad. Supercapacitor. You know supercapacitor? It's very simple for you to know because I just need to charge it and then I ask you to short it. Then you enjoy the moment as telecom or as electronics engineer or technician. Millifarad. So remember that 1 farad is equal to 1,000 millifarad. And also remember that 1 millifarad is equal to 1 exponent negative 3 farad. Let us just try to remind ourselves and avoid any contradiction, right? Then the second unit is called the microfarad. In short, this one is the notation. So remember that 1 farad is equal to 1 million microfarad. Or simply this is 10 exponent 6 microfarad. So for that case, 1 microfarad is equal to 1 exponent negative 6 farad. Okay? Okay. Number 3. Then we come for what? Nanofarad. These units are very important. Nanofarad. So nanofarad, its symbol is this one. 1 farad is equal to 1 billion. 1 billion what? Nanofarad. Simply say that 1 farad is equal to 1 exponent 9 nanofarad. And 1 nanofarad is equal to 1 exponent negative 9, because we have our friends who covered this course who did not go for A-level education. They have just ended in O-level education. You have to train them how to deal with these units, because most capacitors are just mostly electronics capacitors. Most polarized and non-polarized capacitors are in terms of microfarad, nanofarad, and picofarad. So you have to learn how you can deal with just we call them other units of the capacitor. Only supercapacitors which are made in terms of farad. And we use often in case that we want to use capacitor as a source of electric energy. It means a capacitor, just we are using supercapacitors in most cases where we want to replace a battery, especially lithium battery, and use a capacitor as a source of energy. Because a capacitor can be charged and also can discharge. It's just like a battery. Lithium battery can also charge and can also discharge. Are we together? Yeah. Then the fourth unit is called or we call it picofarad. Say picofarad. Are you going to call your firstborn picofarad? Picofarad who? Picofarad Geoffrey. Okay, so 1 farad is equal to how many picofarad? This is a little bit difficult to, it's a trillion, 1 trillion, students here are not confident because they have been dealing with capacity in terms of farad. Capacitance in terms of farad. So 1 exponent 12 picofarad. 1 farad is equal to 1 exponent 12 picofarad. Because this is the 1 billion, right? After 1 billion, next is what? 1 trillion. Trillion, how many zeros does it have? 12 zeros. What if you get 1 trillion? You will tell us, bye-bye. Bye-bye, Dar es Salaam Institute of Technology. We'll meet if God wishes. Bye-bye, Olenjolain and your electronics. I will give you a lift in my helicopter. And I will invite you one day in South Africa in one of my breakfasts. And that actually will be the intimidation to you that you don't have passion with this stuff because money. And then we say that 1 picofarad. 1 picofarad is equal to 1 exponent 10 power negative 12 microfarad. Picofarad. Farad, yes, 1 picofarad is equal to 1 exponent negative 12 farad. So he said that most, so this is the note, most polarized, non-polarized, and a variable capacitors have the capacitance range in microfarad, nanofarad, and a picofarad. So that's why I have taught you in advance. So later when I mention about 1 picofarad, 10 picofarad, it's not a new terminology for you, right? What the capacitance of this capacitor? Sir, that is 1,000 microfarad. 1,000 microfarad is equal to how many nanofarad? It's just 1 nanofarad. It's equal to how much? How many picofarad? Okay, 1,000 microfarad. Yes. It's equal to how many nanofarad? It's equal to how many microfarad? Millifarad? It's 1 millifarad. Okay, fine. What the capacitance of this capacitor? Okay, that is 2,200 microfarad. It's equal to how many picofarad? Just convey it. So you know that what you have to convey in your mind. Okay, this capacitance is what? What is capacitance? Okay, that is 1,000 picofarad. 1,000 picofarad is equal to how many nanofarad? It's 1 nanofarad. How many microfarad? It's 0.001 microfarad. That's how you have to think about it. Class, are we together? Yes. So that is a simple introduction about capacitance. Let me take you into the next introduction or into the next part. Into the next part. So the next part, which it's also it's a added value, it's role or function, role of a capacitor. Before I teach about the working principle, and then I teach about categories of the capacitor, role of a capacitor in AC power. Role of a capacitor in AC power. And here we have a question asking us, this is question 3. What is the role of a capacitor? What is the role of a capacitor in AC power? What is the role? Role means what the function of the capacitor when it has been used in AC power. And they do also practical. How does capacitor behave in AC? In an AC circuit, a capacitor, so this is the role. Stop writing, follow along. A capacitor reverses its charges. Reverses its charges as a current, alternates and produces a lagging voltage. Produces a lagging voltage while it provides leading current. So this is the main role of the capacitor when it has been used in AC power system. Stop writing. When a capacitor has been used in AC power system, this is its role. We say in an AC circuit, a capacitor reverses its charges. Reverses what? As what? As the current alternates and produce a lagging voltage while it provides leading current. These two terminologies that say lagging. Say lagging. So lagging is actually something lagging behind. And leading is actually something leading ahead of the other one. So these terminologies of lagging and leading, we hear them oftenly when a capacitor and inductor used in AC power system. And we taught, because I usually teach, we teach this concept to advanced secondary student in the topic that we call the current electricity and the special part that we call AC theory. Right? In AC theory, it means that actually what the concept behind. The concept is saying this is the voltage and this is current. Right? So in case that we have voltage, this is the signal for the voltage, and also this is the signal for the current, just like this one, for instance, like this. So for this case, we say that current and voltage are in phase. Say in phase. Say are in phase. It means between current and voltage, there is none of them that is leading the other one. Why? Because the angle when time, this is time. The angle here, the angle of current and the angle of voltage, both of them, they start from 0, and none of them, so they start. So it means that when you turn on the on-off switch, then you can find that at the same time, current start and voltage start. So none of them switch is lagging, and none of them switch is leading. Are we together? Class, are we together? How can you have a property of what? Of leading. So the property of leading, suppose that here it is. So you say that, let's say that this is the one of them. So you say that, okay, fine. So for that case, we say that, so we say that here we have another signal, which is in this way. So you can find that this signal is out of phase of these two signals. Right? When you say out of phase, it means that when you turn on your circuit, if this one is leading, if this is voltage, for instance, and this is current, so for this case, voltage is leading what? Current. right? So it means that current is lagging behind what? Voltage. I know these concepts is a little bit challenging to teach even A-level students. I know most of them who have come from A-level, who are watching this video, they have forgotten that concept. They just know how to deal. But actually, if you do remember that you've been dealing with LOC circuit, RC circuit, and LOC-R circuit. So LOC-R circuit, you've been dealing with it. You'll be dealing with capacitive reactance, when you remember, 1 over 2 pi FC. You've been dealing with inductive reactance, which is 2 pi FL. All of those stories are all about lagging and leading. So remember that I know that the A-level students are good in calculations rather than understanding what are the things that are going behind there. But simply let's come back to the capacitor. So when a capacitor used in AC, in AC we have what? Reverse directions of what? Current. Alternating what? Current. We have a positive half cycle and negative what? Half cycle. So when the alternating current is allowed to pass through the capacitor, remember that it's actually what? Alternating. Positive half cycle, negative half cycle. Positive half cycle, negative half cycle. So when AC flows through the capacitor, it causes what? It causes voltage to lag behind. And the currents to what? To lead. What does it mean? So if this is, for that case, this is voltage in the capacitor, AC voltage in the capacitor, and this is AC current in the capacitor. So it means that current is leading, and voltage is what? Lagging. Are we together? And remember from what I taught you in the modules that we call electronic product fabrication, I taught you that most electrolytic capacitors are good conductors of alternating current rather than direct current. Why? Because the electrolytic capacitor offer infinity resistance against the direct current, because the frequency of the DC signal is 0. So if you calculate the capacitance of the capacitance of electrolytic capacitor, it's infinity for DC. It's infinity. So DC will never flow, right? But the capacitance for the AC, because the frequency of AC is not 0, is certain value, which makes the capacitive reactance of the capacitor to be lowered. Are we together? So in this case, we are adding a value. When that alternating current is flowing through the capacitor, what does it do? It causes the voltage to lag behind and the current to lead ahead. Are we together? So in case that you want to design electronic circuit, and the part of that electronic circuit that you need voltage to lag and current to lead, then capacitor is a good electronics components to be used in that circuit. Are we together? If you have a question, you may ask. Number 4, role of a capacitor. Role of a capacitor in DC power system. DC power system. Role of a capacitor in DC power system. What the role of the capacitor in DC power system? We don't, remember this question does not ask you that does DC power flow through the capacitor or does AC power flow through the capacitor? No. So you say when DC power is allowed, Robin, what's going on? Is allowed to flow through a capacitor. Then a capacitor is full charged within a short time. Short time. So it's full charged within it's full charged with the applied voltage. So we say that when a DC power is allowed to flow through a capacitor, then a capacitor is full charged with applied voltage. Applied voltage until it's full charged. So the capacitor is charged. So then a capacitor is charged with applied voltage within a short time until it becomes full charged.